this lesson, we'll begin learning about gas laws. Now, in high school chemistry, we only learn about the simplest of gas laws, and that's what we're doing in these lessons. In the late 1700s and early 1800s is when a lot of the gas laws we're going to be learning about in this unit were first developed. Avogadro was one of the first to do that. And you learned about Avogadro when you did your mole project. Should have, because you had to know about Avogadro's number. Well, Avogadro's number is not a number that Avogadro came up with. Avogadro came up with his hypothesis. And his hypothesis led other scientists later on to figure out the number. What Avogadro came up with was the relationship between the number of elementary particles and the volume of a gas. And what he said was, if the volume of two gases are the same, then the volume, as long as the pressure and temperature are the same, then the number of elementary particles, meaning molecules, are going to be the same in those two containers. What Avogadro found out was, or he proposed in an essay he wrote, was that if you had two samples of two different gases, they're at the same temperature and the same pressure, those two samples will also contain the same number of elementary particles. In this case, elementary particles would be the molecules of a gas. Okay? Well, that was a big thing. Okay? It didn't seem big at the time, but as time went along, it became clear that this was really, really important. Okay, in our understanding how gases behave. You don't even have to know Avogadro's hypothesis, but just for the record, this is what Avogadro's hypothesis looks like. Okay, so N is the symbol we use for moles. Okay, hold on. N is the symbol we use for moles. Okay? Now, if you're writing the unit of moles, let's say you have 12.5 moles, then you write MOL or MOLE. But if you're writing an equation where you want to include moles in the equation, you use the symbol N. Just like we use this symbol T for temperature and the symbol M for mass. The way you figure out density, you put M over V for mass over volume. Well, the same is true here. We don't use MOL to indicate moles in a formula. We use N. Okay, now what you probably need to know is just this version right over here to the far right. Okay, this is Avogadro's hypothesis, but this one down here at the bottom is the same thing, by the way. Okay, if N1 over V1 equals N2 over V2, then it's also true that the ratio of V1 over N1 equals V2 over N2. All right, but generally speaking, Avogadro's hypothesis is written like this: N1 over V1 equals N2 over V2. And that basically describes what Avogadro was describing in his famous essay. Okay. Now, this is the first gas law we're going to be working with and doing math with it. We're not really going to do any math with Avogadro's hypothesis, okay, which now we call Avogadro's law because it's pretty well been established as being true. Charles' law is, Jacques Charles was actually a balloonist, and he figured out there was this behavior going on with the gases in balloons, but he apparently wrote something down. We just don't have it anymore. The only reason we know that he came up with it is because another scientist who worked with gases, Gay-Lussac, said that Jacques Charles came up with it. So the only reason we call this Charles' law is because Gay-Lussac gave him credit for it. Now, Gay-Lussac also came up with the law. Okay, we're not going to have to learn Gay-Lussac's law, but you do have to learn and know Charles' law. Okay, you have to memorize Charles' law. All right. A modern statement of Charles' law is that when the pressure of a sample of dry gas is held constant, the Kelvin temperature and the volume will be directly related. So we have to use Kelvin temperature. We can't use temperature in degrees C.
We have to convert it.
If it's given to you in degrees C, then you'll have to convert it. And you may have to convert it back to degrees C if the question asks you for it. Okay? But the basic relationship is this. If you take the volume of a gas and divide by the Kelvin temperature, which is called the absolute temperature also. Kelvin temperature and absolute temperature mean the same thing. We take the volume and divide by the temperature, we get a constant. And if you change the temperature, the volume will change, So that ratio still remains exactly the same. We still have a K. It stays the same. So the constant doesn't change. So that's where we get this second equation you see down there, down at the bottom, comes from. If I have an initial volume and temperature for a gas, a sample of gas, and I change the temperature of the gas, the volume is going to change to respond, so that the two ratios of volume over temperature will remain equal to each other. And that allows us to do the math we're going to do in using the gas laws we're going to learn about in this class. Okay? Now, here's some symbols that you're going to need to know for the gas laws unit. Okay? You need to know that the capital V stands for volume. You need to know that N stands for moles. We've already talked about those two. And you already know, I hope, that T stands for temperature, because we used that when we were in the thermochemistry unit. Okay? P stands for pressure, capital P. Small letter M, that's mass. Well, we already know that. You should know that from taking physical science and other science classes. K, small letter K, is a symbol for a constant. And actually, there are capital letter K's that are constants, but those are like combined constants. So for us right now, in this simple stuff we're dealing with at the moment, small letter K is going to stand for constant. And the capital letter R is the symbol that we designate for a very special constant we'll get to near the end of this unit, called the ideal gas constant or perfect gas constant. Okay? In the United States, we call it the ideal gas constant. In Britain, they call it the perfect gas constant. Kind of means the same thing. All right, we're going to start with this problem to learn how to solve gas law problems in the manner that you're required to solve them in this class. So here's our problem. If a sample of gas has a volume of 12.25 liters at a temperature of 270.0 K, and the temperature is raised to 300.0 K, what will the volume be? So that you will know what problem you were trying to solve when you look back at your notes, when you're studying for this Unit 7 test, you should be writing this problem down. Okay? So that when you write the solution to it, you'll know what the solution was and why you did all that. It'll be a good example for you to get ready for tests and such. Now, my classes, and I'm sure those of you who've been here all this time know by now, there's a very specific way I want you to do this, right? Yep, because I found that it works better if you learn these step-by-step processes and don't take shortcuts. So here's what I want you to do. In this class, to solve gas law problems, the first thing you want to do is list your knowns and unknowns, or your knowns and unknowns, singular. Most of the time, you've got one unknown. I didn't say how many there were, but I'll show you. The first step is to list the knowns and unknowns, okay, in a very specific way. And then you're going to choose the equation that fits that list. That's how you're going to figure out which equation to use. Now, we'll be going through equation by equation, so initially you'll know in advance which equation you're using. But when we get near the end of the unit and you have to figure out which equation to use, then this process is going to help you a lot to figure out which equation to choose. Then the third thing is to plug in the values that are known. Okay? So, I mean, you've probably done all these things before, but you've not been asked to list them out in such a detailed way before. And when we get to the complex equations like the ideal gas law, you're going to be, well, if you pay attention, you're going to be glad you did. Okay? And then you're going to, number 4 is to isolate the unknown. We're going to isolate the unknown. And then lastly, we're going to solve. Now, when we start out with these kinds of gas law problems, you're going to want to do something you learned in math class, cross multiply. Okay? And I want you to forget you ever learned cross multiply. Okay? Here's the problem with cross multiply. It's a great thing to use. It works very well if you know when to use it. And that last statement is the problem, if you know when to use it. My experience is about 90% of students at this level don't know when to use it. So if you start trying to do cross multiply, you're only going to get most of your answers wrong. Okay? And I want you to get most of your answers right. So I want you to forget you ever learned cross multiply, okay? Do not use it in here with me. If you use it in here with me, I'm going to count it like you didn't do the problem at all, okay? So don't use cross multiply. Got it? All right. Thank you. All right. So the first thing we're going to do here is list our knowns and unknowns. That's the first thing we want to do to solve this particular problem. Okay, we have a volume of 12.25 liters. We have a temperature of 270.0 K. Okay, now, well, I will write T1, but just give me a second to explain why. In reading the problem, it says I have a sample of gas with a volume of 12.25 liters at a temperature of 270.0 K. So that tells you that this temperature, this volume, and this temperature go together. So both of these are ones, V1 and T1. Okay? So you have to interpret the problem. Okay? You have to be able to read for content knowledge. Okay? You can't just read words and let it go in in your eyes and out through the back of your head or something. You got to read for content knowledge here. Okay? All right. Continuing to read the problem, it says, and we have a temperature raised to 300 K. So that's our second temperature. Okay? And it says, what will the volume be if you do that? So yes, this second volume must go along with this raised temperature. So that's what I mean by list the knowns and unknowns. Okay? That's what we mean by list the knowns and unknowns. So the second thing is to choose the equation then that fits. Choose the equation that fits. Well, if I look at V1 and T1 and V2 and T2, oh, that's Charles' law, because those are the variables you find in Charles' law. V1, T1 over V2, T2. Now, right now, you kind of knew that already because we already talked about that's what we're going to be doing. But if you have 5 different types of gas law equations, and I just give you a problem and don't tell you which equation to use, you got to figure it out, and that's what this system works for. Okay? This is Charles' law. Charles' law. Now then, the third step then is to plug in the values that are known. Okay? Well, the values we know are listed up here. So for V1, I'm going to plug in 12.25. For T1, I'm going to plug in 270.0 K. V2, we don't know. So we're going to leave that alone and call it V2. That's our unknown. And we're going to plug in for T2, 300K, or 300.0 K. All right, so that's what we mean by plug in the values that are known. So the next thing is to isolate the unknown. Now we're going to isolate the unknown. This is where I want you to avoid doing cross multiply. To isolate the unknown means we're going to get this unknown. In this case, it's V2. It won't always be V2. Sometimes it's other things. In this case, it's V2. To isolate the unknown, we want to multiply this side of the equation with something that's going to get rid of everything but the V2. Either add or multiply something on this side that's going to get rid of everything but the V2. Do some mathematical operation that's going to get rid of everything but the V2. We're going to multiply by 300.0 K. But, remember, this was an equality. This was two things that are equal here. If I change the equality by putting this over here, I got to do this to the same thing on the other side. Got to do exactly the same thing on the other side. So I have to, if I do it to this side, I got to do it to this side. 300.0 K over 1. Now, this remains equal. As long as I do the same thing to both sides, the equation is still valid. Okay? All right, so let's simplify and see what works out here. Okay? This is where the isolation, I hadn't finished the isolation just yet, because right now the V2 is not by itself. What can I do to the right side to simplify?
Cross out the 300.
Cross out the 300. What else can I do?
Cross out 300.
We can cross out K on this side too. Guess what? Everything's gone except V2. I've isolated the unknown. That's what we want to do. Okay? On the other side, yes, I can cancel out the K's over here. Now we're ready to solve. We've isolated the unknown. Now we're ready to solve. All we got to do is multiply this number times this number, hit enter on the calculator, and then divide, put in this number, hit equals again. This is what we learned to do in stoichiometry, and we learned to do in Unit 1. I told you over and over how to solve these problems. This should be pretty easy by now. All right, so since we're ready to solve now, the answer I get is 13.6111 liters equals V2. Are we done?
No,
Got to check your digits.
V2.
Got to what? We just found V2. We just solved for it. But we're still not done because we don't have the significant digits set up properly yet. How many significant digits?
3.611.
You need 4 digits. I got 4 digits in all 4 of these numbers, all 3 of these numbers here. 1, 2, 3, 4. Underline the last 2 digits, round off. And the answer we want at the end is 13.61 liters equals V2.
Oh, because V2 was... Okay. Dang, my mom is all...
All right. All right, let's do another problem. If 29.7 milliliters of carbon dioxide at 150.0 K is heated to 350.0 K, what will the volume become?
Can you not put me so?
All right, so the answer, if you've solved everything properly, is 69.3 milliliters equals V2. Okay? All right, now while we're on this, listen, before we go on to the next problem, let me tell you some things you got to know. Yes. Let me tell you some things you got to know about solving gas law problems. 1, please listen. You cannot solve gas law problems with degrees C. Degrees Celsius or degrees centigrade cannot be used for calculating the answer to gas law problems. So, if you are given the answer in degrees, if you're given a temperature in degrees C, then you're going to have to convert to Kelvin. Okay? Or, if the problem asks you to give an answer in degrees C, you find the answer in Kelvin first and then convert. So we need to talk about how to convert from degrees C to Kelvin and vice versa. Okay? You need to remember this number, 273.15. You got to memorize that number, 273.15. It's almost as important as Avogadro's number.
What is his number?
This is the number that allows you to convert between Celsius and Kelvin. Okay? And here's how it works. Let's say that I have a temperature in degrees C, like 32.0 degrees C. Okay? That's a hot day. All right? In order to find Kelvin, I'm going to add to that number 273.15 to get the Kelvin temperature. Now, I need to add this vertically. I need to add this vertically to see what to do with the significant digits. So let's take 32.0 degrees C and add 273.15 to it. And by doing it vertically, I can see that I've got an empty slot above the 5. Okay? So when I add these together, I get 1, 5, 5, 305.15, but this 5 is insignificant. Now this is in units of Kelvin now, and we need to round it off to the correct number of significant digits, and we get 305.2 K. So this answer should be 305.2 K.
That's all you gotta do.
That's all you got to do.
Are you sure?
What? What do you mean, am I sure? Like I haven't been teaching this for 15 years. Okay, listen. Now, suppose that you have an answer to a problem in Kelvin, but the prompt says to give the answer in Celsius or in centigrade. Then you're going to subtract. So let's say I have an answer that is 295.4 K. In order to get the temperature in Celsius, I've got to subtract 273.15. So I'm going to go over here and do it vertically. 295.4 K. I want to subtract 273.15. This number? 273.15 is the conversion between...
Yeah.
22.25, but there's that empty slot, so we get 22.2, and this is degrees C now. Okay?
Why is it 9? Oh, we're subtracting.
So to go from Celsius to Kelvin, you add 273.15. To go from Kelvin to Celsius, you subtract 273.15. Okay? To go from Celsius to Kelvin, you add 273.15. To go from Kelvin to Celsius, you subtract 273.15. As somebody astutely pointed out, I rounded this incorrectly. That 5 makes it 2 or 3. It should be 22.3, not 22.2. There you go. Yeah, you deserve the applause. There you go. Only one person applauded, though, but I mean, that's kind of sad. Oh, there you go. All right, good. Good job. Okay. All right, the other thing that will trip you up if you're not careful about Charles' law is that you can't solve directly for temperature. All right, so if I have volume 1 over temperature 1 equals volume 2 over temperature 2, and my unknown is temperature 2, I've got to get temperature on the top of the fraction to solve for it.
Just flip them around.
Good for you. Okay, now listen. What we said a moment ago is, as long as I do the same thing to both sides, you can keep this equal, right? So if I just flip, I have to flip both sides, not one, but both sides. So the way you solve for this, the easy way, is to put temperature 1 over volume 1 equals temperature 2 over volume 2, and now you can solve for temperature 2. Okay? Got that? Huh? You cannot solve for temperature directly. You have to have temperature on the top of the fraction to solve for it. If you try to solve for it while it's still on the bottom of the fraction, you'll get a wrong answer. Okay? All right, then, let's try another problem. What do you say?
No, I'm going to use the bathroom.
Solve this problem, please. Okay. Did you get this for an answer? Suppose we ask you to show your answer in Celsius. What do I need to do? All right. In that case, we'd have an answer.
That's really cold.
Yeah, that's very cold. That's right. Okay? Now, here is the homework problem I want you to do. All right, so in previous instruction, we went over Charles' Law. And we're about to get into some things about Boyle's Law and some things. And Boyle's Law involves pressure. So I want you to know that there are a number of different units for measuring pressure. So if you look here on this sheet I've got here, there are 4 different pressure units. Atmospheres, millimeters of mercury, torr, pascals, and actually kilopascals are also a pressure unit, and kilopascals in chemistry are used far more often than pascals are. Well, you do need to know these things, but you don't really have to memorize them because, yes, as somebody noted, they are on your reference sheet. Okay, but you need to get out your reference sheet if you don't have it out and make sure you know where to find it. That's going to be very important to you. So right here on the very first page of your test references, you have a list of the units and actually the conversion for standard pressure here. Okay, so under standard pressure it says standard pressure is 1 atmosphere, but it's also 101.3 kPa or kilopascals. It's also 760 torr. It's also 760 millimeters of mercury. Those are all pressure units right there. And so what we've done here is to list standard pressure in like 4 different ways that you might use it. Now it has pounds per square inch here. You may know that as PSI. We don't use that in chemistry. Okay? That's an English measurement, and we only use metric measurements. Okay? And standard temperature, if you didn't know, is 0 degrees C and 273.15 K. But you should know it because I've already taught it to you at least once. Okay? It also happens to be 32 degrees F, but we don't use Fahrenheit temperatures at all. And somebody else asked me about this earlier today, but in case you didn't remember how to convert between Kelvin temperature and Celsius, well, it's right there on your test references. Okay? You should know it. That's the only conversion really I asked you to memorize was 273.15. All right. So we have started then with learning about gas laws. I've shown you the method for setting up gas law problems. I've told you that you interpret the problem and make a list of all the things you know along with those variable units or those variable symbols. And then also in that list of the stuff you know, you're going to have your unknown listed there. And then from that, you're going to choose which equation to use. And you're going to write down that equation. Then you're going to plug in the values you know. Then you're going to isolate the unknown in your equation. And finally, you're going to solve. You're going to isolate the unknown and solve for that unknown. And just to remind you, K is a symbol for Kelvin. All right, there's no degrees in Kelvin. It's just K. There are degrees in Celsius. Here's the conversion for Kelvin to Celsius right here. A couple things you ought to know. We've gone over it before in Unit 1. But a cubic centimeter is equal to 1 milliliter. That's the same unit. If you ever see cubic centimeters, that's just a milliliter. Same thing. And it's also a cc. In hospitals, they'll give you a cc of some medication. Well, cc just means cubic centimeter. Okay. We don't use this very much, but a cubic decimeter is a liter. And you need to know that 1,000 milliliters equals a liter because you know that a milli is 1,000 things or 1,000 parts, or there's 1,000 of a milli-unit in a full unit of anything. Okay. And standard temperature and pressure. You need to know what that is. You got to know that by memory. 0 degrees C is standard temperature, and 1 atmosphere is standard pressure. We learned about Charles' Law. We did math problems with that. We learned to solve problems with Charles' Law. Now we're going to be learning about Boyle's Law. We already learned about that in the lab. We found out that with Boyle's Law, there were 2 variables involved. Okay? Pressure and volume. The basic form of Boyle's Law is that, well, when you did the lab, you found out that If you have volume down here and pressure over here, and you keep measuring different amounts of pressure and volume, if the temperature doesn't change, you don't change the amount of gas, because you have the gas trapped in a syringe. So the amount of gas didn't change. The number of moles of gas, the number of molecules of gas didn't change. But all you changed was the volume and the pressure. Even the temperature remained at room temperature. You allowed it to equilibrate. That is to become the same temperature as the temperature around it. And you found that you had a behavior that looked something like this. Okay? That's an inverse relationship. If we were to take all the pressures and volumes that you measured and multiply them together, we were to take all the pressures and volumes that you had in your lab, you'll get almost the same answer every time. In the Boyle's Law lab, I hope you now know that we were looking at pressure and volume. Get out your lab logbook and somebody tell me the pressure and volume measurements you guys got. So we have some lab data and we're multiplying the volume times the pressure here. All right, what you got? 100. Let's say that again.
1111.
Okay.
0.038.
038. Okay, and the third one is 9.8 times 114.59.
1152.98.
All right, now, how many significant digits do I have in these numbers here? Right here. Right over here. 2 digits, right? If I were to round all 3 of these off to just 2 digits, okay? We'll round them all off to 2 digits. All right? I get 1.1 times 10 to the 3rd power every time. All right? So they're awfully close to being exactly the same answer every time I multiply them together. Does that make sense? Okay. Well, guess what? That's what Boyle found out. He found out that if you multiply pressure, as long as you don't change the amount of gas and you don't change the temperature, pressure times volume always gives you the same answer, which means PV equals K. That's the K.
That's a V.
Well, come on. Don't be disrespecting my V's here. Come on.
I wrote down Y for everything.
Really?
Yes.
That's a small letter K too. Okay. All right. Now, listen. That's what he found out. Which means then, in practical terms, that pressure 1 times volume 1 is going to equal any one of these others, isn't it? So pressure 1 volume 1 equals pressure 2 volume 2. And this is the practical version of Boyle's Law. Okay? Does that make sense? Yes? And we have actual evidence of the same kind of thing he got. All right. So this is a practical version of a gas law that we can actually use to calculate for one unknown. When 3 values are known, we can find the 4th value. Let's solve this gas law problem then.
Alrighty then.
Not in this case.
They multiply.
Yeah, this is times. So these values are multiplied together. This times this and this times that. Okay? That's what we did up here. We multiplied them together. Alright? So you're going to plug in P1 is 1 atmosphere times V1 is 1.56. P2 is 3 atmospheres. And V2 we don't know.
V2.
Yep. All right. What was the next problem solution step? If you don't have your notes out looking at this, you're not helping you as much as if you did have your notes out looking at this. Because when you look at your notes, you are helping yourself memorize the problem solution process. Okay? You're going to isolate the unknown. Guys, if all you do is just listen to me tell you this stuff, it's not helping you as much as if you're looking at it yourself. Okay? because hearing and looking multiplies how well you're going to remember it. So if you don't have your notes out looking at that, when I ask you about it, you're just not planning for success, okay? So you should have your notes out looking at those steps, all right? All right, how do we isolate V2 then? V2 is the unknown. How do we isolate it? Yes?
You have to multiply the atmosphere on what is that, L? Liters. You have to multiply that, then you divide the atmosphere on the right.
Okay. All right, so what we're doing, what he's describing is essentially dividing both sides of the equation by this value here.
Yes, but you have to show that you divided each side.
You have to show each side being divided. Exactly.
But then, I didn't do that on the quiz because I just figured it out. So, yeah.
What you do to one side, you must do to the other. And the reason we're dividing by this is because that means that it cancels all of this out. So there's the dimensional analysis part of the problem solution process, okay? We were teaching you dimensional analysis from Unit 1, all right? And that's the reason I'm using this method here is because I want you to remember canceling out units, canceling out species whenever you can. Over on the other side, we can cancel out atmospheres. We have V2 all by itself. Now we're ready to find what V2 is. It's just a matter of plugging the numbers into the calculator. Okay? Okay, how many significant digits do I need in this answer?
3.
Who said 2?
3.
I'm just kidding.
I look at the number on the right.
It's the total number of digits. 1, 2, 3, 1, 2, 3, 1, 2, 3. This only has 2 digits that are significant. Leading zeros are not significant. How do we rectify that problem?
You gotta divide.
No. What do we do to get 3 significant digits? Put a 0 on the end. That's it. Guys, you have to be smarter than your calculator. Your calculator is just a piece of equipment. All right? It's made of plastic and metal. Has a battery in it. It's got some paste in the battery. All that. It's just a piece of equipment. Okay? You're an organic thinking being here. Okay? You've got to be smarter than that calculator.
You're making the calculator look so bad.
Well, the calculator does a lot of good stuff, but there's some things the calculator doesn't do well.
Like this one thing, but everything else I can do.
Well, I don't know. Look, a calculator can't tell you that your answer is unreasonable. Okay, a calculator can't tell you that you don't have enough significant digits or you do. Actually, there are some calculators that can, but you got to know how to tell the calculator what to do. The thing is, when you look at an answer, you need to be able to make a judgment about whether it's a reasonable answer. And if we don't have enough significant digits, it's not really a reasonable answer. Okay, but that is the final answer for this problem. Okay. All right, so let's solve this problem, guys. This is a different problem for you to solve. I walked you through the first one. Now it's time for you to do one.
First, you state all the knowns.
Yes, you're right.
Then you plug in the knowns.
Can you cut?
Yes, you're right.
All right, there we go. Got a guest teacher here.
Hi, my name is Dr. Janiyah Cohen.
Boo!
You know what? I can't use your name on
Who
here.
said boom?
Oh,
So we have to
you
cut
just
that
gonna crop
off.
it out? You gonna crop it out?
Yo,
I'm
Yes.
sorry, Mr.
why you look like?
Okay,
You can use a fake name. You can even use your first name, but just not your last name.
okay. This is Diana Blackwell.
Please be quiet
Making
and
racist
listen.
jokes about me.
Please pay attention. This is your responsibility to pay attention and desist.
Right. This is the problem we had, and we're gonna solve it. Now let's start with step 1. Let's isolate the unknown factor. So we're gonna cross out the liters, and now we have pressure 2 by itself. The same thing we do to this side, we have to do this side.
I'm even talking to you.
Crop that out.
Can you go ahead and cross out the leaders, please? On that side.
I did this. Okay.
Instead of that side, the other side.
All right. Let's do some calculations here. And we gotta take the okay, yeah, this is the right problem. I was about to say, Miss Tedder, this is not the right problem. Okay, I'm wilding. Okay, so we're gonna take this atmosphere and multiply it by the volume. Okay. Let me pause. Let's multiply the top and divide it by the bottom. And the top is 0.860, and we're going to multiply by 11.2. And what do we get? Anybody? Somebody. No.
When you do the whole thing.
She hasn't divided yet.
Oh, well.
She's giving you the final answer here. That's what he's doing over there. He's giving you the final answer.
So what do you get for the whole thing?
Okay.
Okay. Now we get, yeah, that's what we get. So now we're going to divide it by 15.1.
50.0.
Yeah, that's what I meant to say. 15.0.
You get 0.642.
There you go.
And the answer we got was 6421333.
Okay, that's
Now
a
we got a-
continuous number. Y'all can tell that, right?
Yeah.
The rate's going to continue. What marking do you use to show it's a continuous
Yeah,
number?
line.
So put a line over one of the threes there, and it just shows everything continues. You don't have to keep putting threes on there.
Okay. I don't
That's
know.
what she did. It's okay.
Okay, and now we have to round. Let's see. I rounded from right here to here.
That's right.
No, that's right. So now I got 0.642.
You forgot the arrow.
0.642 atmosphere. And so P2 equals.
Good. That's it. All right. Nicely done.
Even though I did all the work.
Oh. So we've talked about Charles' law. And we said Charles' law was V1 over T1 equals V2 over T2. We've talked about Boyle's law. And that was P1 times V1 equals P2 times V2. When we first started talking about Charles' law, I told you that another scientist, whose name was Gay-Lussac, was the first person to write down Charles' law. Now, he attributed that law to Charles, and that's why we call it Charles' law. But Gay-Lussac had his own law.
That's really funny, Mr. Tech. Say it.
And his gas law, the gas law for which we give the name to, is P1 over T1 equals P2 over T2. We won't be doing any direct equations using this law because what we're going to do next will allow you to do it even if you don't have that law. So in fact, you can use the next law and do all these equations, all these problems. What we're going to do is combine all these laws together. Okay? You notice the similarities? What's similar in these laws?
They all have the P, V.
There's V's in these two laws, there's P's in these two laws, there's temperatures in these two laws. So what we're going to do is combine all that together. So we get this, P1 V1 over T1 equals P2 V2 over T2. Okay?
And what law is that?
Tedder's law. No, it's not Tedder's law. This is
Mr. Tedder, I know you're working on one, though.
combined gas law because we combine them. Okay? The combined gas law. Okay. Here is a combined gas law problem. Now listen. Listen carefully. First thing you're going to do is make a list of what you know and what you don't know, right?
Yes.
And so just do that. Do one step at a time. A journey starts with a single step. Okay? So what do we know here? We know volume 1. Okay? What else do we know here? We know temperature 1. We know that that temperature can't remain with those units, can it? You have to change it into Kelvin. What else do we know? We said that already.
Volume 2.
Well, what is volume 2? It's asking for volume 2. What else do we know? We know the pressure, the first pressure. Okay, what else do we know? Huh? Read the question carefully. We know the, huh? We know 2 different temperatures and 2 different pressures. Read this question. Okay, so what does STP stand for? And you should know what those are. So that's your second temperature and pressure. Oh, it ain't that hard. Just think about what the question's asking you and what it's telling you. Okay? All you need to do is to figure out what the second temperature and the second pressure are, and those are always known because they're standard. Okay, we looked at that earlier in this lesson.
Is it STP second temperature pressure?
Just said that.
It says that we're changing the volume. It's asking what the volume is when you're at standard temperature pressure. Well, I gave you earlier, I showed you, I reminded you earlier. It's not that I taught you the first time because I've taught you before what standard temperature pressure are. Okay? But you just have to plug those in. Okay? I hope you got all that in your notes, but it's also on the front page of your test references. The biggest problem I see when I walk around and look at your work, guys, is people skipping steps. Okay? Okay, if you always do all the steps, you're almost always going to get the right answer. First thing you got to do is write the problem down. If you don't have the problem written down, how can you figure out what your knowns and unknowns are? Shh, please be quiet and listen. Please be quiet. I mean, that's probably not helping you much either when you're talking when I'm trying to tell you how to do things. Okay? Pay attention. All right, so from the list, from the question that's written down, we have 2 liters of gas. That's the volume. You've got 25.0 degrees C. That's the temperature. And you've got 745 millimeters of mercury. And then you have a second temperature and pressure indicated by STP. STP is standard temperature and standard pressure. Standard temperature is 0 degrees C. Standard pressure is 1 atmosphere. 1 atmosphere is also 760.0 millimeters of mercury. Standard temperature is also 273.15 K. Okay? So from that, then we need to make a list of knowns and unknowns. So that's what I did here. Here's the volume in the problem. Here's the temperature in the problem. Here is the pressure in the problem. Here is the standard temperature mentioned in the problem. Here is the standard pressure mentioned in the problem. All you got to do is write this stuff down and take it step by step. Okay? That's how you solve problems. Step by step. Okay? So, 0 degrees C is 273.15. I showed you that earlier. It's on the front page of your test references. 1 atmosphere is 760 millimeters of mercury. I showed you that earlier. It's on the front page of your test references. The only thing we need to worry about is we can't solve problems with temperature in degrees C. So we've got to convert that into Kelvin. And to do that, we take that 25.0 degrees C and we add 273.15 to it. And we add them together, we get 298.15. We've got an empty slot here. That digit there, that 5 there, means that is insignificant. The empty slot makes it insignificant. So this is in Kelvin now, and we're going to round it off to 298.2 K, which is what this number is. This number here, this measurement in degrees C, is this measurement in K. All right? Now we have everything we need to start a problem. We're going to write down the equation. Well, we got V1, T1, P1, V2, T2, P2. And the equation we're going to use for that is the combined gas law. That's the only one that has those variables. So P1, V1 over T1 equals P2, V2 over T2. That's the next step. Then the next step after that is to plug in what we know. Well, we know pressure 1. In fact, I'm going to use a pen to kind of make it a little bit smaller so I have some room to do things. 745.0 millimeters of mercury. We know V1, it's 2.00 liters. We know T1, and we've got to do the Kelvin temperature, 298.2 K. On the other side of the equation, we know P2, it's 760.0 millimeters of mercury. Let me just take a quick aside here. I could put 1 atmosphere here, but when I do the math, I won't be able to cancel out millimeters of mercury if I do that. So I want to have my units of pressure and temperature and volume to all match. Okay? You've got to have all your units of measurement matching. All right, so we don't know V2. That's what we're trying to find. And we do know temperature 1. That's standard temperature, 273.15 K. Now, to get the unknown here by itself, we're going to do the same thing you did for Charles' law and for Boyle's law. For Charles' law, we had to multiply by something. For Boyle's law, we had to divide by something. That's all we're doing. Same math. So we're going to multiply by 273.15. Actually, it should be 2, shouldn't it? I'm sorry. I didn't have the right digit here. That's got to be 2 there. Okay. 273.2. So we've got to multiply both sides of the equation by 273.2. So I'll multiply this side by 273.2. And then I've got to divide by 760 millimeters of mercury. Okay, pay attention. Simplify. 760.0 millimeters of mercury is canceled by that. All that cancels out. 273.2 K is canceled by 273.2 K. I have V2 by itself. Okay? Over here, can you simplify this?
Yes.
Do it. Kelvin cancels, millimeters of mercury cancel. We're ready to do the math. Okay? So we're going to take 273.2. We're going to multiply that by 745.0 and multiply that by 2. Okay? 273.2 times 745.0 times 2. Okay? And now we're going to divide by 760.0. So divide by 760.0. Hit enter and divide by 298.2. Of course, I'm just not going to write down all those digits. This calculator I'm using here has way too many digits to deal with.
My calculator stopped there. So 3, 6, before the 7.
How about I'll stop right there? Is that good enough? What units of measurement do I have left? Liters. Does that measure volume? Yeah. No, I haven't rounded it off yet, but it does, this unit of measurement does measure volume. What that tells me, AJ and Janiyah, is that I most likely set it up right. If my units of measurement match the variable I'm looking for, I'll probably set it up right. Well, how many significant digits do I need here? 3 digits, thank you. I didn't even see that. What's my problem? So 1.80 liters. Okay. All right, there. Now, listen, please. Listen, please. Okay. Guys, just follow the steps. That's really all there is to it. Just follow the steps, okay? All right, let me give you a homework problem solve. That's homework. That's it. What's its original pressure? Now that's the original volume. What's the original pressure? It doesn't tell you. It just tells you divides in half, doesn't it? So you can choose any pressure you want to start with. Read the problem. Now if you can use 1 atmosphere if you want standard pressure, you have 1 atmosphere. You can do that. That's right. That makes it easy, doesn't it? But you can use 760 torr and use 1/2 of that, right? For the final pressure. What's the beginning temperature? Pretty much whatever you want it to be. I'm gonna look and see if you half your temperature and your pressure. That's all. And it's really simple. And don't make it harder than it has to be, guys. Don't make things harder than they have to be. That's right. Yeah. What? What now? Sure.